No fish has ever been found in the deepest 25% of the ocean. Not because we haven't looked, but maybe they cannot survive. And yet, here lies the paradox. In the deadliest zones, acidic, pitch black, crushed by unimaginable pressure, life persists. Always. It eats bones with acid. It drifts on falling marine snow, silent and slow. It rewrites the rules of biology just to survive. So what has changed? Why, at a certain depth, does evolution stop? Is this the ultimate boundary of life, or just another illusion we haven't yet decoded? If you had to choose, what would you believe? An absolute biological limit, or a mystery still lurking in the abyss? Comment 1. To begin the descent into the depths where science starts to doubt itself. 90% of us think the deep ocean is a place of absolute starvation. Wrong. At depths where light vanishes completely, food doesn't disappear. It just becomes merciless. So what does life do? Wait, hunt, or recycle, death. From the surface, marine snow drifts down like the ashes of life-decaying organisms, waste, fragments of organic matter falling slowly through the water column like an endless rain. It sounds abundant, but across the vast ocean floor, it's barely enough to survive. Evolution has no choice but to innovate. The vampire squid does not chase. It opens sticky filaments, releasing them into the darkness, collecting every tiny organic particle. No pursuit, no struggle, just patience. Elsewhere, a whale carcass crashes to the seafloor, an island of death. And zombie worms appear. No mouth, no stomach. They drill into the bones, secreting acid, dissolving the hardest structures to feed symbiotic bacteria inside. They eat with chemistry. At the top of the predatory chain, the beaked whale plunges into the dark, emitting sonar, mapping its surroundings with echoes, then sucking prey into a single, precise strike. Clean, efficient, devastating. 3 strategies, 3 paths to survival. Yet all answer the same question. When food vanishes, what do you become? Which path would you choose? Comment 1 if you are the hunter. Comment 0 if you choose patient waiting. The deep ocean's cold is often called its silent killer. But if that's true, why does life not only survive, but thrive? After solving the problem of food, evolution faced another challenge. One far crueler, far colder. The temperature here doesn't just dip low. It touches freezing, even below 0 degrees Celsius, a realm where water can crystallize inside living tissue. It should have been the end. But it wasn't. Evolution struck back with a paradoxical strategy: go giant. In cold waters, oxygen dissolves more readily. Bigger bodies mean more surface area for gas exchange. Tiny creatures elsewhere here, they balloon into monstrous forms. Sea spiders, giant isopods, colossal squid, big enough to survive. But size alone isn't enough. Another silent threat lurks: ice crystals in the blood. Just a shard, enough to rupture cells instantly. The solution? Antifreeze proteins. These molecules cling to ice as it begins to form, halting its growth before it can do lethal damage. A mechanism precise, almost flawless. And then, one creature went further than all. The ice fish. No red blood cells, no hemoglobin, no color. Instead, it breathes directly through skin and gills, absorbing oxygen from the frigid, gas-rich water as if its body were a living membrane. No red blood, no old limits. The cold was defeated, or at least delayed. Because deeper still, another challenge waits. Not just lethal to life, but capable of breaking the very chemistry of existence. You think seawater is the same everywhere. Wrong. At the bottom of the Mediterranean, there are lakes hidden inside the ocean. Blocks of hyper-saline water so dense they refuse to mix, forming sharp boundaries like a coastline in eternal darkness. An ocean within an ocean. But this is no place for casual exploration. This is a graveyard. Along the lake's edge, life clings on. Step past the boundary, and everything changes instantly. Not because of oxygen shortage, not because of crushing pressure, but because chemistry turns against you. To understand why, you need a simple principle: osmosis. Every living cell maintains a delicate balance of water and salt. Enter a hypersaline environment, and water is ripped from the cell at lethal speed. Proteins warp, enzymes halt, entire biological systems collapse. Fast, silent, irreversible. A. Bodies don't die from attack. They dissolve from the inside out. The lake floors are littered with these salted corpses, preserved nearly intact for decades. A graveyard frozen in time. But evolution, as always, finds a way. It discovers an exception. The hagfish, a creature straight out of a nightmare. When threatened, it ejects a colossal layer of slime. Thousands of protein threads explode outward, mingling with mucus to form a dense gel that envelops its body. A biological cloak, a chemical shield. The slime slows water exchange, protecting cells from osmotic shock. Not perfect, but enough. Enough to step into a realm where every other creature dies instantly, then crawl back out. Not stronger, but smarter. Yet the question remains: if life can overcome even treacherous chemistry, where does the real limit lie? We've survived hunger. We've survived cold. We've survived poison. But pressure? That's different. It doesn't chase you. It crushes you. In the Hadal zone, deeper than 6 kilometers, pressure reaches 1,000 times what we feel at the surface. Every air-filled cavity in a human body would collapse instantly. Bones wouldn't snap, they'd compress. Cells wouldn't die, they'd deform. So, what did life do? It didn't fight. It surrendered. Creatures here abandoned all rigid structures. No thick bones, no gas bladders, no pockets that could be crushed. Their bodies are soft, gelatinous. Pressure passes through, it doesn't destroy. No resistance, no confrontation, just adaptation. At the microscopic level, the war is even deadlier. Pressure doesn't just squash bodies. It warps proteins. It tears apart the most vital cellular machinery. This is where chemistry begins to fail. And evolution deployed its ultimate weapon, TMAO, a tiny molecule acting like an invisible wedge, sliding into proteins and holding them in shape as pressure tries to collapse them. Without it, life halts immediately. Keep the structure. Keep life alive. But what happens when that very solution becomes the problem? If you've followed this deep enough, you're approaching the true limit. The point where it's not pressure, but the very chemistry of life itself that betrays it. No fish lives deeper than 5 miles. Not for lack of trying. Not for lack of adaptation. Life has engineered molecules, reshaped proteins, invented chemistry to defy Hadal pressure. But here there is a limit. The secret lies in TMAO. It's the deep-sea fish's shield, holding proteins intact as the ocean's crushing force tries to annihilate every cell. Without it, digestion stops. Respiration fails. Reproduction grinds to a halt. TMAO keeps the fish alive. But there's a cost. Bodies become hyper-saline. With every meter deeper, salinity rises. Eventually, the gradient reverses. Water rushes in instead of out. Osmosis becomes lethal. To survive, fish must pump continuously, expelling massive volumes of water impossible under Hadal pressure. Bladders collapse. Energy drains. Metabolism collapses. TMAO predicts a hard ceiling. Around 5 miles deep, the very molecule that protects becomes the executioner. The paradox of nature. And right at this edge, life still clings on. Snailfish drift in gelatinous bodies. Dumbo octopuses flap fragile fins. Sea pigs graze the abyssal mud. Flexible, adaptive, surviving. But go deeper, and vertebrate fish vanish. Chemistry draws the line. No adaptation, no mutation. No evolutionary trick can cross it. The molecule that holds proteins also holds the fish back. The deepest recorded fish? Just shy of this invisible boundary. Just a few hundred feet from the abyss. So, what impresses you more? Life's ingenuity or the limit evolution cannot breach? Comment 1 for life's brilliance, 0 for the ultimate boundary. The deepest ocean teaches a brutal truth. Some limits are physical. Some are chemical. And some define the ultimate frontier of life itself. Life finds a way. Again, the deepest fish has hit the limit. But life never stops. Below the Hadal zone, where pressure crushes bones and TMAO saturates every cell, vertebrates vanish. Not by chance. By chemistry. And yet something survives. Something soft. Something tiny. Giant, single-celled protozoans drift silently through the near absolute darkness. Amphipods cluster in swarms, hundreds in a single 3-hour sweep, exploiting niches invisible to the naked eye. Each single cell stretches nearly 4 inches across, defying all expectations of size, structure, and energy. No backbone. No skeleton. No breath. Only chemistry. Osmosis and intelligence encoded in DNA older than most continents. But how? How do these organisms withstand pressures that would crush a human? How do they maintain cellular integrity when TMAO, the lifeline for fish, turns catastrophic in excess? The answer remains elusive. Perhaps alternative molecules? Perhaps metabolic pathways never before observed? Perhaps strategies evolution has yet to reveal to science. And their existence matters. They prove that the Hadal Zone is not a dead ocean. It is a laboratory, a stage where biochemistry is pushed to its absolute limit. The story of vertebrates ends at the chemical boundary. But life continues. No pursuit. No struggle. Just persistence. Life always finds a way. It conquers hunger. It endures bone-chilling cold. It adapts to killer salinity. Every obstacle, every brutal trial of the deep ocean evolution has an answer. Vampire squid harvest marine snow. Zombie worms dissolve whale bones with acid. Sperm whales hunt in absolute black with echolocation. Life refuses to surrender. But then came the pressure. And the chemistry. Not darkness. Not freezing cold. Not food scarcity. The true barrier hides in the very molecule that keeps them alive, TMAO. This molecule shields proteins under crushing pressure, preventing them from folding, breaking, or ceasing to function. Without it, deep-sea fish can't digest, can't breathe, can't reproduce. It is their savior and their prisoner. The deeper they go, the more TMAO accumulates. The data is clear. Extrapolated to the Hadal Zone, a number emerges just over 5 miles below the surface. Beyond that, the salt balance flips. Water rushes in. Cellular machinery collapses. No bladder. No urine excretion. No energy left to survive. The very molecule that enables life becomes the ultimate limit. Nature solved hunger, cold, and salinity. Elegantly. Relentlessly. Each solution a masterpiece of survival. But pressure and chemistry? They write the final line. Yet just above this molecular boundary, life endures. Soft-bodied squid, Dumbo octopuses, sea pigs, all surviving where vertebrate skeletons would shatter. Surviving. Adapting. Exploring. Just enough to reach the edge of the impossible. Which strategy impresses you most? The vampire squid's patient hunt? TMAO's chemical mastery? Or the endurance of the deepest octopus?
We are the same now. Join
Comment
us
1 for
in the
predator.
deep.
Comment 0 for patience. Because below this molecular limit, vertebrates vanish. But life? It continues. And the ocean has only just begun to tell its story. The ocean doesn't end where the fish stop. Pressure crushes. Darkness reigns. Chemistry conspires. Yet life persists. Soft-bodied squids drift nearly 4 miles down. Giant microbes flourish where no vertebrate dares. Cells adapt. Molecules bend. Survival finds a way, again and again. The limit of fish isn't the abyss. It's physics. It's salt. It's TMAO. And just beyond that line, something else begins. Something smaller, stranger, unbroken. The deep sea is not merely hostile. It is a boundary marker, a line between the possible and the impossible. What mysteries lie below that line? What molecules? What strategies? What life forms are waiting to teach us the next rule of survival? Comment 1 if you believe life always finds a way. Comment 0 if you think some limits are absolute.